So problem 1 says determine the following limits. So we have the limit as x is going to infinity of a polynomial over a polynomial. So the numerator is going to infinity and the denominator is going to infinity. So we actually have an indeterminate form of 0 over 0. So we need to do something more work before we can evaluate this limit. So what we're going to do is we want to take advantage of our special limit we were given, or our important fact. And it was that the limit as x approaches positive infinity of 1 over x to the r equals 0 whenever r is positive. So the name of the game here is going to be let's find some zeros. So I don't have any fractions within this giant fraction that I have, but I can actually create as many of these as I want to find. So the algebra move that we make here is we multiply the numerator and denominator to make it legal, right? Whatever you do the numerator, you have to do the denominator. We multiply by 1 over x raised to the highest power of x that we see anywhere in the problem. So this is x to the 0, x squared, x to the 5th, x to the 1, x to the 5th. So since 5 is the highest power we see anywhere in the equation, I'm going to multiply the numerator by 1 over x to the 5, and then I need to also multiply the denominator by 1 over x to the 5. So the limit as x approaches infinity, I'm now going to distribute this all the way across the numerator. So negative 2x to the 5th, when I multiply it by 1 over x to the 5th, the x to the 5s cancel, and I just get negative 2. 7x squared over x to the 5th, the x squared cancels, and I end up with 7 over x cubed. 12 is just 12 over x to the 5. The denominator, when I multiply that across, gives me 1 plus 17 over x to the 4th. Now I can invoke my special limit. So the limit of negative 2 is just negative 2. The limit of 7 over x cubed is going to be 0. 12 over x to the 5th is 0. And in the denominator, I get 1 plus 0. And this simplifies to negative 2. So this would be the answer to my limit. But if I wanted to interpret this answer in any way, we now know that looking at limits to positive infinity is telling me how this graph is behaving on its right side. So this graph actually would have a horizontal asymptote at y equals negative 2 on the right side. So the right edge of the right-hand behavior of the graph on its right edge is that there is in fact a horizontal asymptote. This special limit holds even when we're going to negative infinity. So if I look at this next function, it says that the limit as x goes to negative infinity, we have a line on top and a quadratic on the bottom. So this is still an infinite form, or indeterminate form, of infinity over infinity, right? Some version of infinity over infinity. So I do need to do more work before I can evaluate it. So now when I scan this for the highest power of x, I see I have an x squared in the denominator and an x to the 1 in the numerator. So you choose the highest power, which was x squared, and whatever I do to the numerator, I have to also do to the denominator. Now, when I multiply across the numerator, I get the limit as x approaches negative infinity of 3 over x plus 7 over x squared, and the denominator is 4 over x squared plus 1. Now I can invoke my special limit, and the numerator gives me 0 plus 0, the denominator gives me 0 plus 1, which just works out to be 0. So this, if I wanted to interpret this, this graph has a horizontal asymptote at y equals 0 on its left side. So the left edge of the graph is approaching 0. The last one is the limit as x goes to negative infinity of a polynomial. And believe it or not, right, this is why I made the note in the intro video that you cannot do this by direct substitution. So if you took this negative infinity and you plugged it in here and then plugged it in here, how do you know when you're adding and subtracting infinities from each other, right? We have some negative signs going on. How do we know what we're actually getting? So we can actually still use our important fact. So what we can do in this situation is we could factor out the highest power of x that we see. So I'm going to write this as the limit as x goes to negative infinity, and I'm going to pull a negative x cubed out front. So this just leaves me with 1. When I pull an x cubed out of this, I get negative 1 over x squared, and here I get positive 2 over x cubed. I can check that I've done this right by distributing this back out, and I should get this. So negative x squared times 1 is negative x squared. Negative x cubed times 1. Negative x cubed times 1 over x squared. The x squared is canceled, and it leaves me with positive x. Negative x cubed times positive 2 over x cubed. The x cubes cancel, and I'm just left with 2. So I did, in fact, factor this correctly. Now if we look at this, if I take a negative number and I plug it into x cubed all by itself, it stays negative. Negative times negative times negative. But then I have to take that negative result and multiply it by negative 1, which now makes it positive. So infinity cubed is still infinity. And then using my special limit, I get 1 minus 0 plus 0. So the final answer to this limit is infinity. So we would actually conclude there's no horizontal asymptote, right, as x approaches negative infinity. And that f of x increases without bound as x decreases without bound. So the y values that come out of x grow to positive infinity, increase without bound, as we look to the left, so as x decreases without bound.